Here's an example we did in class where we used proportions for areas and map scaling. So in this example, we had this little triangle. There was a map of Seattle, Portland, and Boise. And in the map scale, the distances on the map were 1.5 inches, 4 inches, and 3.5 inches. And we know that the actual physical distance is 400 miles. So intuitively, you can kind of figure out that the scale, the ratio, is 4 inches is 400 miles. So 4 over 400 or 400 over 4, whichever way you want to think about it. The ratio is from 400 to 4 inches to 400 miles. So 1 inch is on 100 miles. Divide both sides to get a nice unit. And then if we want to use that scaling factor, we want to know proportionally what's 1.5 inches from Portland to Seattle. So 1.5 is clearly 150. So again, the numbers work out nicely. So you can do a mental scaling proportional idea to figure this out. How do you do it algebraically? Well, we would have set up a proportion. One way to do that is this would be the Seattle to Portland side. And we want to compare that to the Seattle to Boise side. And the numerator is the physical distance. The denominator is the map length, 1.5 inches. We could do it upside down with the miles in the bottom and the inches on the top, but the unknown x miles, we want to put in the numerator because keep your variable in the numerator. It's easier than a variable in the denominator. You just have to multiply it across. So set it up a fraction like this, and you can easily solve algebraically, multiply both sides by 1.5 and by 4. So you cross multiply, and we get, again, wonderfully 150 miles for this. So you can set up these proportions in multiple ways and solve for them. Another example we did in class was the telephone pole and the shadow of that. And it says that a telephone pole casts a shadow that's 50 feet long. So that's the 50 here. And we don't know how tall it is. It asks, that's the main question, how tall is the telephone pole? To compare, we have an 8-foot traffic sign that leaves a 10-foot shadow. And these are similar triangles because the angle of the sun is going to be the same. So if you remember your geometry, if they're right angles, angle, and then the third angle has to be the same too by geometry, but there's an angle formula that says the two triangles are similar. And if they're similar, that means their lengths are proportional. So there's two ways to think about that proportion. Like I've said, you can think about the height over the shadow for the pole and the sign. That's the height over the shadow is x feet over 50 feet for the telephone pole and 8 feet over 10 feet for the shadow. So we have that relationship. Or we could switch and think about the big over the small. So here we've got the height. The height of the big thing, the telephone pole, is x over the height of the shorter thing, which is the street sign, which is 8. And on the right, we've got the shadow. And so the ratio of the shadows is 50 to 10. So intuitively, you can think, well, okay, the shadow over here is 5 times as long. So it's 5 times as tall. So if this is 8, this one has to be 5 times 8. Algebraically, you can set that up as a fraction like this. Here, 50 over 10, that's our 5 times as big, multiplied by 8, and again, you get x equals 40 feet for the height of the telephone pole. Great. But you can set those proportions up in either way, whichever one makes your algebra easier. A more complicated example we talked about was the time and the speed problem, the distance and rate problems that we've talked about. We've done these a couple times, but let's see if we can talk through this one. What I tried to say in class is what's the big picture equation here? What's equal to what? And it says Danica can sail her boat 5 miles into the wind, so the wind is slowing you down, in the same amount of time as her return trip. So the time with the wind equals the time against the wind. And we've talked about how time is distance divided by speed, miles divided by miles per hour. And so what's her distance with the wind? She goes 5 miles. And if she goes X miles per hour in her boat without the wind, this is her speed with the wind, against the wind. X miles per hour, 7 mile per hour wind. And so that thing, that fraction on the left is her time, her hours to go 5 miles against the wind. Then she turns around and she comes 12 miles with the wind. And so we got the 12 miles and her speed. Now the wind is pushing her faster, 7 miles an hour faster. So her speed is now X plus 5. So after all is said and done, we have that purple box, a nice rational equation. And so to solve that, here using your intuition isn't going to be hard because that's a more complicated expression. We've got x's in both sides. Multiply both sides by the least common denominator. In this case, that's going to be x minus 7, x plus 7 on both sides. As we've done before, some things cancel on both sides, and we're left with this expression. Distribute x times 5 and 7 times 5, 12 times x, and negative 7 times 12. Add and subtract. So I subtracted all the x's to the right-hand side, so I would have positive 7x. And I subtracted all the numbers to the left-hand side, so I get 119 equals 7x. Divide, and x is 17. And as I said, when you're doing word problems, 17 what? That's 17 miles per hour. So that's the speed of Danica without the wind helping or hurting. And double check that that makes sense. So check by plugging that into the original equation in the purple box that we had. 5 over 17 minus 7, that's 5 over 10. 12 over 17 plus 7, that's 12 over 24. Those are both equal to a half. And so that's, it works, it's true. But those are a half what? That's a half an hour. 5 miles at 10 miles an hour is a half an hour for both trips. So that's great. We can set up a rational equation and solve it like that. Let's do a third one, another one that's slightly more complicated. So let's read it first. Read it, it's important. Victoria jogs 12 miles to the park along a flat trail, and then she returns by jogging along a hilly trail that's 20 miles long. She jogs 1 mile per hour slower on the hilly trail than on the flat trail, and her return trip takes 2 hours longer. Find the speed, the rate on the flat trail. So first of all, like I said, what's the overarching equation? What it tells you is her return trip is 2 hours longer than her the flat time. So oops, that's a minus. So if the flat time takes longer, subtract 2 hours from that and you get the fast time, which is on the flat course. Okay, so now we can plug in what we know, the facts we know, into how long did it take her to run 12 miles on the flat course? Well, 12 miles at X miles per hour, which we don't know how fast she is, that's the variable we're looking for. That's the number of hours it took her to run on the flat trail. What about this? That's 20 miles, the distance on the hilly trail divided by the speed on the hilly trail, which is a little bit slower, minus this 2 hours, which is the difference in the times. So great, you set up this box, that's your equation. And now rewrite it and see if you can simplify and solve. It's a rational expression. We've got 2 fractions, and we've also got this one thing that's not a fraction that's just hanging out there. But still, we multiplied by the least common denominator on both sides. And that's going to be x times x minus 1. And so we multiply by x times x minus 1 on both sides. Here on the left, what cancels? The x cancels with the x, and we're left with 12 times x minus 1. On the right-hand side, we have to be careful and distribute. So we've got this whole thing times 20 over x minus 1, which just leaves 20 times x. And we've got that whole thing times a 2. So don't forget that last part, 2 times that new common or that denominator that we cleared out. Now you've got an expression that is simpler. There's no fractions, no rational expressions. So it's just a matter of distributing, multiplying everything out, grouping like terms, moving everything to one side, factoring, and setting the terms equal to 0. Easy as that, those steps. So multiply everything out, we get this blue expression. Be careful with your negative signs. Make sure you distribute the negative through there, for instance. And then I moved everything over to the left-hand side to set it equal to 0. And everything, all the constants were multiple of 2. So I factored out a 2 in front. X squared minus 5x minus 6. That we can factor. And you get 3 parts. And they multiply to give you 0. So one of those 3 has to be 0. 2 equals 2 is 0. That never happens. There's 2 equals 0. That never happens. X minus 6 equals 0. That means she was jogging at 6 miles per hour on the flat course. Then that would have been 5 miles per hour on the hilly course. Okay. This one means she's jogging at -1 miles per hour. Doesn't make sense in our context. So toss that out. So the answer is she was going 6 miles per hour on the flat course. So again, let's just double check all that algebra works out. Plug it back into your original equation. And if we plug in x equals 6, we get 12 over 6, which means it took her 2 hours on the flat course and 20 miles. And now she's going a little slower, only 5 miles an hour here on the hilly course. That's 4 hours. So that's 2 hours longer than on the flat, faster course. So the algebra works out very nicely, and you can solve all of these.